Good morning, everyone. As Tom mentioned, my name is Zaid. I'm part of Accenture Research Lab. Today, I'm going to share with you some of the research project that I was involved in around predictive maintenance and prescriptive maintenance. So just briefly, Accenture Lab is the R&D lab of Accenture. Accenture is a large consulting company. We're an applied research lab, so we essentially look at incubating new technologies, and we look for breakthrough applications in these new emerging technologies. We have 7 different research labs globally, one in San Francisco where I'm located. We also have one in Washington, D.C., one in France, Dublin, and a few other locations in Asia and the Middle East. Some of my personal research interests are around probabilistic programming systems. It's kind of a new emerging paradigm in modeling and doing automatic Bayesian inference, causal inference, and more specifically around the application of these methods outside of biology. And finally, stochastic optimization. And by that, I don't mean kind of the gradient descent type of stochastic optimization, but more along the lines of sequential decision-making under uncertainty. So the rest of the talk will cover 2 of these topics, probabilistic programming systems and stochastic optimization in the context of predictive maintenance. So to motivate the talk, this use case came to us from a client of ours, Charity Water. They are a nonprofit organization. They operate globally as well. Their mission is to provide access to clean water to developing countries and remote locations. So what they do is they install these water pumps. They're hand manual water pumps in remote locations. And for a very specific region in northern Ethiopia, they went the extra mile where they designed a custom sensor to kind of make the pump more smart and connected to the cloud. And they have about 3,000 of these water pumps cloud connected with the sensors installed. And they are now kind of managing this, one of the largest water networks in the world. So the insights you get from this water network is really big value. So I have a picture here of the sensor. It's custom designed for this water pump. And one of the key things that they were thinking about when they were designing the sensor is they don't want it to make any major modifications to the pump. So a technician with a hand wrench can be able to take the pump apart, install the sensors, and put it back together. They're also responsible for the maintenance of these water pumps. So 3,000 different locations. They have different technicians geographically spread, and sometimes they respond to failures, but sometimes they're on a schedule, so they check 1 or 2 pumps a day. So that's kind of the maintenance side of things. So when we looked at this problem, this kind of inspired us to come up with a solution that is a little bit more data-driven and a little bit more predictive, and that kind of inspired this research project. So this kind of describes a prescriptive maintenance problem, and it's a very common problem. Any company with geographically spread assets where they are worried about predicting its failure and also optimizing the operations around the maintenance it will be applicable. So this problem is not just specific for Charity Water. It's applicable to a lot of different companies, and it's a very hard problem. So you have uncertainty around the state of the health of the asset. So a lot of times sensors are imperfect and there is a lot of noise coming from the sensors. A lot of times you're unable to put the sensor in the right location. So the measurements that you're measuring are not giving you kind of direct estimates of the health. They're indirect. There's also dynamic uncertainty. So this is uncertainty around the operations, the future operations of the asset. So how does it change over time? How do people use it over time? That's another aspect of uncertainty that we have to take a look at. There's also multiple objectives that kind of play at odds. So on one hand, you want to maximize the utilization of the asset. So you want to run it for as long as you want. Right before the failure, you want to do the replacement or the maintenance. But on the other hand, you don't want to run it until failure because the failure has a very high cost. There's more problems with this prescriptive maintenance type of setup, but those are kind of the main ones. So to solve this problem, we kind of broke it down into 3 different subproblems to handle this high dimensionality. So first, we need a degradation model, so a model that estimates the health status of the asset and can predict when it's going to fail. So we'll talk about that in a little bit. We also need a maintenance policy, so how do you determine the best action to take given the current status of the asset? And at the end, you also want some sort of a resource allocation policy, which determines who is the right resource to go and fix the right asset. So the rest of the talk is structured by kind of going through each one of these subproblems. So first, we'll talk about the degradation process model. So just to give you some context, the high-level problem statement, you have historical data coming from the assets, and these are usually time series data. And you also have some historical failures. So for some assets, you've recorded the failure time. And a lot of times, the number of failures is very, very small, especially in highly reliable systems. You don't really get to see a lot of examples of failure. So this is kind of a property of this problem, is that the failure rate is very small. And we're going to fit a model to that data, and then we're going to use this model to not only predict the failure time of the currently operating assets, but also for any newly installed asset, we want to be able to predict the time of failure. And I'm sure a lot of you are familiar with how an IoT type data set looks like, but I wanted to emphasize on one point here that typically you have some sort of a time vector and some sensor data coming over time. But here I'm plotting the time series in a vertical way, which is kind of a weird way to look at it. But usually you're sampling at a fixed frequency, and a lot of times this frequency is low because you're worried about bandwidth and the cost of sending the data to the cloud. So when you're sampling at a low frequency, a lot of times you miss the moment of failure. So you record the data right before the failure, and then the next time you go and sample, you actually miss the failure. So you don't have observations at the time of failure, you have observations right before it. And this becomes a problem when the sampling frequency is low. So a classification type of solution would not work well in this scenario because you cannot really learn this relationship between the distribution of the data and the class failure class because you don't really have observations at that time. So our approach to this problem is using kind of graphical models and hidden Markov models. So we rediscovered hidden Markov models a couple of years back, and we really like how flexible these tools are. They're very well understood. They're interpretable, and Bayesian techniques can be used in doing the inference as well. So we really like these types of models. So at a high level, you can imagine an asset being in a healthy state, and that's state A, and that's when you first install it. And then when it fails, that's the failure state, the F state. And as it goes through its life, it's kind of bouncing around these different states, and these states are hidden, and our goal is to learn these states from data, from observations. Different states represent the different levels of degradation of the asset, and each heartbeat in this video is essentially a time step, and that could be a minute, a day, a week, depending on the problem. And from data, we're able to learn these transition probabilities. So the size of the arrow that you see on the screen represents the transition probabilities. So you learn that from the data. You also learn the distribution of each one of these states. And what's nice about this is that once you learn the model, you can kind of pause at any point in time, and you can ask the model, okay, can you propagate the state in the future? And because this is a terminal state, a hidden Markov model with a terminal state, you will always end up in the failure state, and the time of that occurrence is your expected failure time. So it fits really well for modeling failure or degradation mechanisms. I won't bore you with the details too much, but at a high level, a hidden Markov model is defined by 3 variables: pi, which is the initial state probabilities, the state transition matrix, which is a kind of an end state by end state matrix, and a state observation distribution, which kind of defines the observation distribution of each one of the states. And all of this is learned from kind of sequences of observations coming from the asset. Some useful properties. So I think I mentioned the first two already. We use the terminal state as a representation of the failure. The rest of the states are just different levels of degradations, or states representing different levels of degradation. One key thing we like about these models is the fact that you can incorporate expert knowledge in the failure mechanism by putting constraints on the transition matrix. So for example, since I know this is a degradation process, I might make an assumption that the asset can only get worse. It cannot get healthier on its own. So I will not allow any transition from a later state to an earlier state. And that's a constraint that you can put on the model to incorporate some of your knowledge about how the system is moving and changing. A bonus point here is that you also gain some performance on the training because you kind of get rid of some of these computations. So you actually gain some performance benefits from putting these constraints. These models can also handle the right censoring of the data. So the right censoring is essentially data sets or a property when you've not observed the failure for all of these assets. So you've observed the asset right before the failure, so you know it survived up to a certain time, but you don't know when it failed. And this is a key property of these survival type of data sets, and these models can handle that very well. And a question came up yesterday in the Microsoft talk in the morning around anomaly detection on how can these models handle different rate of arrival for the observations. And these models can handle that very well. So you would assume the data is coming at a fixed rate. And for the timestamps that you actually have an observation, you use the observation. And the timestamps that you don't have an observation, you assume it's missing. And in the forward probability computation, you can handle that very, very easily. So missing data is completely fine. So here's an example of how this inference would look like. So assuming you have a time series data, and then the bottom plot shows this inference, how we do this inference over time. So we're trying to infer the hidden state. So this is a posterior distribution over your hidden state. But this is done in a sequential manner. The data is kind of streaming in, and you're trying to make an inference about the hidden state. So that was done for the entire sequence, but in practice, the data is streaming in, and you have to make these prediction and inferences a lot of time in real time. So how does that work? So here I have 3 plots that show our prediction of when the failure will occur, but after observing certain parts of the time series. So the first one shows that how our prediction on when the failure will occur after observing about 110 time units worth of data. So you can see that's the black dot. And the red dotted line is when the failure actually occurs. And what you'll notice here is that the more data you observe, the better your failure time estimate. And this is something we expect from these models. We expect that the more data you see, the better your estimate of where you are in the chain, and then therefore you can forecast when you'll end up in the failure state much more accurately. And also on the bottom, like between each plot, there's this lightly shaded plot. It's kind of a tile plot. And this shows our forecasted state. So at each point in time, I am asking that the model, what will be my state at a certain point in time? And you can see, for example, you're in the green, and then you jump to the red, to the purple, and then to the brown. So you can see this is a very flexible model. It's not just, for us, it's not really just about accuracy. It's about having a robust model that you can kind of ask all these different questions and running this in real time. So this is all good if all of your assets fail in the same way, but a lot of times they don't. Especially when you have assets geographically spread, different location might fail differently, and different locations might use the asset differently, and maybe weather conditions can play a factor. So a lot of times there are kind of hidden groupings within the data. Different assets fail differently. And the way we handle that is we build this much, much bigger model where we allow it to infer these hidden groups automatically from the data. So if you look, this is kind of an example of a model where there's 3 different groups. And these groups are essentially, each one of them will describe a different degradation process, but it's all part of one model. And each one of these groups, as I said, will have a different profile, different degradation profile. And this can also be explained by the survival curves that you can build from these different models. So for example, the profile A will probably have a different degradation profile, meaning it will have a different survival curve compared to another profile B. And all of this is kind of learned from the data. You don't really know what profile A and B and C is. You allow the model to figure out what these different profiles are just by observing the data. So an asset will fall under one of these profiles, and you make that inference as you're observing the data. And here we have a trick of how to avoid overfitting, because when you build these large complex models, you run a risk of overfitting. So we use a trick that was kind of borrowed from the LDA type models, if you're familiar with that, where we use mixture distributions, and the base distributions in these mixture distributions are shared across states. So that kind of regularizes the model and avoids overfitting. I don't want to say avoids overfitting. It kind of reduces the risk of overfitting. So yeah, I mentioned the survival curves earlier. Once you learn the model, you can kind of ask it all these different questions. So one of the things that you can do very, very quickly is to look at the survival curves. And just by looking at the survival curves, I can learn so much about my assets without even kind of feeding it any data after the learning. So for example, we learned 3 different profiles, and each one of those you can compute the survival curve. So for example, the blue one is the best one because it has kind of the slowest failure rate. But the red one and the green one, they kind of have similar behavior. One has a high failure rate in the beginning, and it slows down later, compared to the other one, which has a slow failure rate in the beginning. That's the red one, and kind of speeds up later on. So just by looking at the survival curves, which is a very simple computation to make, once you learn the model, you learn so much about your assets. One other kind of neat trick that you get from these models is this concept of profiling. So this is a concept borrowed from kind of the marketing space, where you build profiles around your customers, but here we treat assets as our customers, essentially. So as you're observing more and more data, you're essentially profiling the asset, and you're trying to figure out what type of profile it belongs to as the data is streaming in. So in this example here, the middle plot shows that we're very unsure about which profile this asset belongs to in the beginning, but as we observe more data, the green profile seems to be more prominent, and then we know for sure that this is the right profile. And at the bottom plot, this is the entropy, which is kind of an estimate of the uncertainty. And you can see the entropy is high in the beginning, and then it kind of drops as we observe more and more data. So you can use this, for example, when the entropy is high, maybe you shouldn't make a decision. Like if we go back to the marketing space or the marketing example, if the entropy is high, maybe I shouldn't send a marketing campaign to this person because I don't know much about them. But when the entropy drops, we have a much better estimate of what type of profile this customer is or this asset is, and then maybe you should send the campaign, or the marketing campaign. Okay, so now we talked about the model and what you can do with it and the different levels of complexities. Now we need to talk about testing these models. How do we measure performance? And it's also a very tricky problem because accuracy is not enough. There's many different dimensions to the performance. So you can predict the failure before it happens, so that is one metric. You can predict it after the failure. You can also make the prediction with varying lengths of observations. So what's my performance is like when I observe 50% of the data compared to 20% of the data. So there's a lot of different dimensions to measuring the performance of this model. So we came up with this kind of a simpler way to measure it, which is borrowed from classical statistics, the ROC curve, but it's not really an ROC curve. We call it kind of the failure time, the mean uptime versus failure rate curve. It's not the nicest name, but it looks like a hockey stick curve. On the x-axis is the mean uptime, and the y-axis is the failure rate. And the way it works is like this. So you take your data, and you go through each one of your assets, and you feed it through the model, and you ask the model, OK, what's my probability of failure tomorrow? And if it's above a certain threshold, you assume that the asset will fail, and you kind of do a replacement. So you take it offline. But if the asset fails before the probability of failure reaches that threshold, you take that as a hit, and that's kind of a failure that you missed. And we go through all the assets, and we record how many times we missed the failure. And we also record the mean uptime of the assets, so how much utilization we got from the collection of the assets. And that will end up as a data point on this plot. And then we do this again for different thresholds. So if we go from 0.01 to all the way to 0.99 on the probability threshold, and you end up with this curve. So you can see there's a clear trade-off. You can be on the lower left side of the curve. That's the sensitive part. You will not miss a lot of failures, but you also don't get too much utilization out of your assets. But you can operate on the top right of the curve where you get much more failures, but you also get more utilization out of the assets. And here I tried to fit different models with different complexities and different hyperparameters just to see how the different curves would look like. So you can clearly see the orange one is the best one because it has kind of the lowest failure rate and the highest asset utilization. If you think about what we just did, when we did this performance estimation or performance evaluation, we essentially came up with a policy. It was a simple policy, but it is a policy. We decided that if the probability of failure is above a certain threshold, we're going to replace the asset. So that kind of takes us to the next step, which is the maintenance policy. And we're lucky that because we used a hidden Markov model as our model of failure, there's a very nice extension to it that allows us to do these policy learning, which is the POMDPs, the partially observable Markov decision processes. And those are kind of a hybrid or combination of Markov models and Markov decision processes. Hidden Markov models and Markov decision processes. And it's very simple, actually. A lot of the parameters of this model you already have from the HMM. What we need is to define a cost estimate or cost function. And we have to define what are the different actions, maintenance actions I want to take. So here I defined 3 actions. One is do nothing, so I don't want to do anything about the asset, a repair, and a replace. And each time I'm in a state, I have the option to take an action. And this action will take me to the next state. And when I reach each single state, I get a reward or a cost. The negative reward is a cost for us. So you can think of it, this is not just kind of economical cost, but also social cost. So if I go back to the charity water example, losing access to water for certain communities, that's a big social cost rather than economical cost. So when you formulate your problem as a POMDP, you can solve it. And when you solve the POMDP, you get a policy. This is what you learn by solving the POMDP. And this policy is essentially a value function. It tells you what's the value of each action that you could take at each level of uncertainty, given the probability of where you are on this chain. So to make this more concrete, here's an example. So this is kind of a simplified version of this policy. This is not a real policy. This is just for demonstration. The next slide shows a real policy. So you can see it's a kind of a piecewise linear. So each action gets its own linear function. And on the x-axis is the probability. Think of it as the probability of failure. So if the probability of failure is closer to 1, then the best action to take, the one that has the highest value, is the no maintenance. And if the probability of failure is closer to 1, then it's the replace. And when we solve the POM-DP, you're actually learning these curves. You're learning the slopes of these curves. And in high dimensions, these become hyperplanes and gets more complex. So, we're learning these. As we're observing more and more data, we're looking at these posterior distributions. We can take a slice of that, and that is essentially, you can ignore the other states, and let's look at the failure state. And that has a certain probability. We feed that into our policy, and that will give us that this is the best action to take. Versus if you take another time slice, that will have a different probability for failure. And if you feed it into the policy, it will give you a different action. So this is how the policy would work in practice. And you can, this is a policy that is local. So it's not looking at the entire fleet of assets. It treats each asset, it gives you the best action to take on each individual asset. This is a picture of a real policy. So because it's high dimensional, I can only plot 3 dimensions. So these are high dimensional or hyperplanes. And this is the value function, essentially. So I have 6 different planes. Each plane represents an action. And the y, or the z-axis in this case, is the value of that action. So you can see, for example, if you are operating, so the x and y will be your different probability estimates of the different states. So we have, in this example, I had 6 different states, but I can't plot all 6. I can only plot 2. So you can imagine, given what the probability estimate is, you're at one point on this plane, and that will give you the value of the action which has the highest value. And the blue one is the repair one, the red one is the replace, and all the other curves, all the other planes are the kind of do nothing. And the cost that went into this policy, we had a failure cost, a repair cost, and a cost of replacement. So you don't really actually have to define too much information about your cost. Very little information is enough to really learn this policy. And how do you define the cost? This is kind of an art on its own. So you would have to sit down with the experts in the space and really figure out what is it really, how do we put the number on the cost of failure? How do we put a number on the cost of replacement? I mean, the cost of replacement and the cost of repair is more straightforward because you have to take into account how much it costs for an asset and maybe the travel time to it. But the cost of failure, that's where it gets more tricky. But you eventually can solve for the policy. You get these value functions, and then you feed it these probability estimates from the hidden Markov model, and then you get the best action to take. So that gets me to the last piece. So we saw how we modeled the degradation. We're able to predict the failure, or we have a way to predict the failure. We take that estimate and we feed it into our policy. The policy will give us what is the best action to take on each one of the assets. But now we need to figure out how to run the maintenance operations. So now that we know what the demand is, this becomes a resource allocation problem. You have limited number of resources and a changing demand, and you need to kind of match the demand with the resources while minimizing cost. So at a high level, you have resources. These are kind of your technicians. They're geographically spread. You also have changing demand. So now instead of each asset having 1 in 6 states or 1 in 20 states, because we fed in the policy, now we turn that high dimensions into only kind of a replace or repair. So this reduced the dimensionality significantly. And your goal is to assign the right people to the right demand, given that you have changing weather conditions, for example. These are your constraints. So certain part of the network maybe is inaccessible, so you have to put some constraints on the system. There's different levels of inventory, so maybe different resources or different technicians have different skills. So how do you kind of match the supply and demand while minimizing overall cost? So this is a kind of a classic resource allocation problem, and we use ADP, or approximate dynamic programming approaches. It's kind of similar to the POMDP, where you evaluate or estimate the value function, but the state space is much, much bigger. I won't kind of go over the details here, but at a high level, you have to define some sort of a state variables. So these are your resources and your demand. You also have to define your decision variables. So this is kind of which resource to go and maintain which asset. There's exogenous information. So this is information that arrives between the last time you've taken an action until the next time you want to take an action. So we usually take actions at discrete time steps, and all the information that arrives between these two different time steps, this is all kind of random. This is the randomness in the system that we have to take into account. We have a transition function. This is usually a deterministic function. And we define an objective function. And we also use piecewise linear approximation so that we can take advantage of these kind of really high performance linear programming solvers. And when you think about these problems in really high dimensions, you would need these approximations. Otherwise, the problem becomes intractable. So the last thing I want to share here with you is that we are turning this research project into kind of a web app now. We're working with an outside firm to kind of build a UI for us around this. So I just wanted to share some of the progress that we've done on some of these mockups. So it's still kind of low fidelity mockups, but we're making some progress into putting a web app behind this research project to make it a little bit more user-friendly. This concludes my talk. Appreciate your attention. Thank you very much.
Are there any questions for Zaid? I'll bring the mic to you.
Thank you. That was a very nice, clear talk. You said something about probabilistic programming.
Yes.
Do you have an opinion on like where the state of the art is and where it's going, and PyMC3 versus 4 and all that? Where do you see things going, and where would you put your resources into that right now if you had to choose?
I see. Yeah. So I've been looking into that recently very extensively. The tool that I use the most is the STAN tool, but these are kind of for purely statistical problems. I recently started to look into, of course, PyMC3 is a very kind of robust tool as well. So STAN and PyMC3 are, I think, one of the best tools. They're very well tested. One of the emerging tools that I really like is GEN, coming out of MIT. They are treating this as not just kind of a probabilistic programming system, but also they're looking at the inference as well. So you can actually not just do statistical type of models, but also do even like if your problem is image type of analysis, or one of the examples that they give is you want to infer the 3D pose from a 2D image. You can use that system to do just that. So GEN, I think, is a very promising project. And also there's another project called Turing, which I've used in the past to do hidden Markov models, because they're thinking about it as one of the examples that they use in their benchmarking is a time series example, and they use a hidden Markov model for it. So I think that the tools that are very well tested are the STAN and the PyMC3, but the new emerging ones, I think this GEN language is also written in Julia, which is also a very interesting place. But yeah, very good question.
Thank you very much for a very good presentation. How many examples of failure do you need before this becomes a viable approach?
Oh, actually, I mean, I don't have so it depends on the nature of the failure mechanism. So if the failure mechanism is very clear, or it's not a very difficult failure mechanism, then you don't need a lot of examples. Because what you really need is just few examples of the system transitioning from the previous state to the failure state. So if you've observed it just few times, that's enough to build some sort of an estimate. And the rest of the chain, you have plenty of data to learn. So, I mean, I don't really have a definite answer for that. It really depends on how difficult it is to model that degradation process, that process itself. But we've tested this with 1% failures. If you have 1,000 assets, only 1% of them you actually observe the failure, and that was good enough.
Thanks for your talk. That was really interesting. I just wondered if you were able to map any meaning onto the hidden states, B to E, to the physical state of the pump.
Right. So there's, this is a very, some people argue that these states are completely, not interpretable. And you can also think of these states are very interpretable. I'm on the other side of the argument. I do think these states are interpretable, especially if you spend time modeling the structure of the model very well. So if you spend time thinking about the number of states, for example, if you spend time thinking about what transitions to what, and with these graphical type models, you don't need, you can run it fully unsupervised, you can do it completely supervised, and you can do it kind of somewhere in the middle. So as long as you incorporate as much information in the model, then the states can be interpretable and can have a meaning.
So
Yes.
Can you comment on the implicit stationarity assumptions that are being made here, and
Right.
and how in today's systems there's constant software upgrades, different components that have very different failure rates that
Right.
affect the overall system. Can you comment on that?
Right. So I think the right approach there is to take a look at each component separately. So you treat each component as its own entity and its own asset, and you model it separately. So this way you don't run into these issues where different components are affecting, one component can affect the other component's failure rate, right? And on the stationarity question, I mean, that's the assumption you have to make. So maybe we spend some time trying to pre-process the data to make it closer to a stationary process rather than something else. So I don't know if that answers the question, but we can chat about this offline.
So my question is related to the previous two. So
Yes.
I also do predictive modeling,
Yes.
and I've observed that in many cases you have a very widespread about failure modes. So it could happen
Yes.
that it fails immediately because something breaks,
Right.
or it could be long degradation. So how do you choose the amount of hidden states in order to model this?
Right. Yeah, that's a very good question. So typically what we use, we try to treat the number of states as a hyperparameter. So we use techniques from like the Bayesian optimization literature to try to figure out what is the right number of states. But you're right. I mean, a lot of times the asset can fail in many different modes. There's many different modes of failure. So you can treat the number of states as this hyperparameter. And then when I talked about earlier having these different profiles, those could be different failure modes. So, but how do you determine the number of these? That's kind of the art there. You can also use Bayesian optimization to treat that as another hyperparameter. Say how many different failure modes exist in this data set. The model becomes really, really large, but it is possible. Like these models really scale because you can learn them through kind of traditional Bayesian methods, but you can use expectation maximization to learn these, and that these models or these algorithms are distributed. So you can distribute the computation on many different nodes using Spark or any of these tools, and you can really fit really, really large models, and they do scale. Yeah.
Zaid, are you able to tie any of the degraded states to actual physical states? Like, let's say a piece of the pump has broken off. This might not actually inform the replace process, but might better assist with resource allocation repair.
Right. Yeah, that's a good question. I mean, you would. I mean, I guess it also depends on the problem. You would hope that some of these states really represent true physical state of the asset, but I think it depends on where the sensor is located. So if the sensor is located in a location where you're actually measuring certain parts of the asset that represents the physical conditions of the asset, then those states should present the physical state of the asset. But if it is in kind of these weird locations and all you're getting is noisy estimates of some health, then it might not. So it really, I think this depends on, first, like the location of the sensor, where it's located, and also the nature of the failure. Is the failure caused by complete kind of randomness, or is it caused by kind of outside factors, right? So you think of an asset coming out of a factory. There's random variation in the performance of this asset just due to randomness in the manufacturing process. And that's completely random, right? But there's also external factors, and that will kind of change the shape of that survival curve. So yeah, I think it does depend on where the sensors are located and the kind of the nature of the failure itself. Yeah.
All right, let's give one more hand for Zaid.
Thank you.